Hello everyone, welcome to this video on improving performance in Snowflake. My name is Pat Lucas and I'm a Tableau and Alteryx consultant at the Information Lab and part of Data School Cohort 22. Today we'll be discussing some of the features that Snowflake has included in order to improve query performance in the background. We'll also touch on how you can take advantage of some of Snowflake's features to further improve query performance. And we'll also delve into some simple SQL statements and how you can manipulate your SQL language in order to further improve that performance. And this won't be necessarily restricted to Snowflake. This can be used with other databases as well. I just thought it'd be good to touch on that since we are discussing performance in general. And if you are watching this video, I'm going to assume you know a bit about Snowflake. You've had the general introductions and you know what the platform looks like and how to use it. If you don't, then there are many videos on the Information Lab's YouTube channel for you to dive into before you look at performance. So without further ado, let's dive into our first topic. So choosing a sensible warehouse size. Here we have our 4 Snowflake warehouse size examples, the extra small up to the large. The outer purple coloured bracket is the warehouse. Within the warehouse, we have the blue square, which is our cluster. Within the cluster, we have our servers. So first and foremost, choosing the right warehouse size is really important for performance because the larger the warehouse, the more compute resource is available to compute your queries, particularly if they are complex and power intensive. So each warehouse size doubles up the number of servers that are available and can be used for your queries. If you are computing complex queries, these can be shared across multiple servers within a cluster, meaning that your query will run much faster with more servers. So to put this into context, 2 servers is likely to compute a query around twice as fast as 1 server. But obviously, with the larger the warehouse size you have, the more it will cost per second of runtime because you are using more compute. But the idea here is that if you have a large warehouse, the query will compute much faster, so the runtime of your warehouse will be considerably shorter, and so you have this kind of tail-off between cost and time. But how do you choose this sensible warehouse size? Admittedly, when you first implement Snowflake into your organization, it's going to be difficult. You don't know how much compute resource you're going to use, and you don't know what size is going to fit your organization perfectly. The best thing to do is take a bit of an educated guess to start off with and then really monitor how your queries are performing. If they're not performing too well, this is a sign that you may need to upsize. If they're performing incredibly well and you find that your costs are a bit higher than you hoped, then downsizing would be your best option here. So just to recap, it's really important to put some time and effort into monitoring your usage and performance when you first implement Snowflake. It will tell you whether you should upsize or downsize and will improve your costing as well, so you're not charged more than you need to be. So the next feature we're going to be talking about is scaling out. Scaling out is the process of adding more clusters to a warehouse, and this is very useful when there's a large number of concurrent queries running. Scaling out allows any queued queries to be executed on the new cluster or clusters if more than one cluster is added. So scaling out will create this multi-cluster warehouse. And multi-cluster warehouses are only available on the Snowflake Enterprise Edition and above. So scaling out really isn't an option to anyone that has the Snowflake Standard Edition. So in our example above, we have 3 queries we're wanting to compute. And for the sake of this demonstration, let's pretend they're all pretty power intensive and they require a lot of compute resource to run. We have a small warehouse, which means each cluster has 2 servers, and one of these queries is currently being computed within that cluster while the other queries wait in a queue. Now, when you first created your warehouse, if you set the maximum number of clusters to be greater than 1, Snowflake will automatically scale out your warehouse when required, which fires up additional clusters to help cope with the additional compute required by the queries you've made. So this means that instead of waiting for each query to run within the same cluster, one after each other, They can run concurrently within different clusters, and therefore this can hugely decrease runtime, hence improving query performance. This is a great example of an automatic Snowflake feature which helps improve your performance. All you need to do is set the option to increase the number of clusters if necessary when you create your warehouse. You don't need to do anything when you're running your queries or you have queries in the queue. If you need additional compute, Snowflake will automatically scale out your warehouse, provide that additional compute, and your queries will run much faster. So before I move on to more performance improving features of Snowflake, I just wanted to discuss the scaling out methods. So here is an example of how you can set your minimum and maximum cluster counts when you create your warehouse. Here we have a minimum cluster count of 1. So when our warehouse initially fires up, it will have 1 cluster, and we have a maximum cluster count of 3. So if we need that additional compute resource, if we need a second or a third cluster, Snowflake will automatically scale out our warehouse to ensure that the compute resource meets the demands of our queries. The syntax here is quite simple, and we're just going to briefly talk about these two types of scaling out methods. So the maximize method is when you set your minimum and your maximum cluster count to exactly the same value, and that value has to be greater than 1. Therefore, whenever your warehouse starts up, the same number of clusters will be available the whole time to deal with the queries that you want to execute. It won't change because your minimum and your maximum are the same. This method is generally used when you have quite a predictable usage pattern within your business. For example, if you know that your team will all log on at 9 AM, begin computing queries, and then stop at, say, 11 AM, so your warehouse will shut down at 11, it may be useful to have a specific number of clusters in place to just deal with the compute required. The maximized method is much less common than the autoscale method. So the autoscale method is where Snowflake will automatically scale out your warehouse when there are queries queued. Snowflake will do this according to the minimum and maximum values you set, as we've discussed. And this method is considerably more common and certainly more cost-effective. Now, with the scaling out method, there are 2 different scaling policies that come with it: the standard and the economy. So with the standard scaling policy, a new cluster will start immediately when a query is queued, and it will shut down after 2 or 3 consecutive checks. And these consecutive checks are carried out at 1-minute intervals. So if there are no queries being run or being queued on the new clusters that had fired up, after those 2 or 3 consecutive checks, those extra clusters that were added will be shut down. The other policy is economy, and this is when a new cluster will start only if the system anticipates that the cluster or clusters that are in use will be kept busy for at least 6 minutes. So if the system anticipates that the clusters that are in use will be used for, say, 4 minutes, it will not fire up those new clusters. It will let the queries compute, and then the queued queries can then compute after those on the same cluster. And the economy scaling policy will shut down after 5 or 6 consecutive checks. And again, these consecutive checks are at 1-minute intervals. So I just wanted to round off the topic of warehouse sizes and scaling out on performance in Snowflake by talking about our multi-cluster versus our standard warehouses. So on the left, we have an extra small multi-cluster warehouse, which has 4 clusters, and that means we have 4 servers in total. And on the right-hand side, we have a standard medium warehouse, again with 4 servers, but all within the same cluster. Now, if your organization has a lot of users computing a lot of queries concurrently, you'd want to go for the multi-cluster option. That will avoid queues for your queries. Any queries that are in the queue will be able to run on those extra clusters that are fired up. And if you still have quite a lot of queries, but they are power intensive, then you probably want to scale your warehouse up to maybe a medium or a large size warehouse. If your organization has few users, but they compute quite power intensive or complex queries, then you'd probably want to stick to a standard warehouse, but you'd want to scale this up to maybe a medium or large. And this is because when you scale up, the number of servers increases, and queries can compute across multiple servers within the same cluster. So the more servers you have within that cluster, the more compute resource you have to compute a particular query. And if you don't have too many of them, then you don't need multiple clusters. And just to reiterate, queries can't compute across different clusters, but they can compute across multiple servers within the same cluster. So let's move on to our next topic, which is micro-partition pruning. So micro-partitions in Snowflake are units of storage that hold table data, and each of them contains around 16 megabytes of compressed data. So in this case, pruning relates to eliminating micro-partitions. So pruning will take place when a query is run containing a where clause, or when you don't select all of your columns of your table. Snowflake will only scan the micro-partitions that meet the conditions of your filter, and so will prune the remaining partitions, meaning that the data that is pruned will not be scanned at all. So because all the data isn't scanned, queries are able to run much faster, and therefore being more performant overall. But how are these partitions set up? So on the screen you can see our initial table, and this table that we load into Snowflake will be chunked up into various micro-partitions, and how these look will be based simply on the ingestion order, so the order that you ingest your table into Snowflake. Therefore, ingestion order directly impacts your query performance, and so to promote best query performance, ensure your table is ordered in some way, preferably by a column or columns that you often filter by. In our case here, we have our table ordered by our ID. So when our micro-partitions are built, we can see that they're chunked up into their IDs. So we have 1 and 2, we have 3 and 4, and 5 and 6 together. So if we run a SQL query that just is searching for any ID that's less than 3, it will not scan the bottom 2 and just scan the top 1, making the query run a bit quicker. And ideally, if you run a query that filters to about 10% of the data, only 10% of the micro-partitions will be scanned. And it's the partition metadata that enables precise pruning by storing min and max values for each column. It's also worth being aware that once created, micro-partitions are read-only. So you cannot edit a micro-partition, and the only way to change a partition is to create a completely new version of the table, which creates new micro-partition versions. Alternatively, there are clustering keys that I will talk about in a few slides' time. So let's look at a visual example of what Snowflake does when a query is run with a filter. In this case, we are filtering to the ID being less than or equal to 2. So Snowflake immediately prunes 2 of the micro-partitions because the metadata tells Snowflake that they don't have any data that needs to be produced in the query result. On top of micro-partition pruning, Snowflake also compresses columns individually within micro-partitions. So for the micro-partitions that are left after pruning, only the columns referenced by a query will be scanned, further reducing the data that Snowflake must scan to produce the result, hence improving our query performance. Obviously, this example on the screen is on a very small scale, since we only have 6 rows and 3 columns of data. Snowflake tables may consist thousands or even millions of micro-partitions. So how these partitions have been set up becomes more and more important the larger the table you have. So you can actually learn about how well your table is clustered into different micro-partitions because Snowflake has the following functions. The first is system clustering depth, and this computes the average depth of the table according to some columns that you specify. So the result of this function just produces one number. And the smaller this average depth, the better clustered your table is with regard to those specified columns. The second is system clustering information, and this returns all the clustering information, including the average depth, the total count of partitions, and a partition depth histogram. And I won't go too much into that in this video, but what the histogram shows you is essentially it gives you the idea of the distribution of overlap depth for each micro-partition in the table. The less that my micro-partitions overlap, the better your table will be clustered. So alongside the average depth, the histogram is a key piece of information in telling us how well a table is clustered. So from these functions, if we notice that our tables aren't clustered very well into micro-partitions, or if we notice our table is quite large and performance is degrading over time, what we can do is set up clustering keys. Now, clustering keys are subsets of columns in a table and are located within the micro-partitions. So they tell Snowflake how you want your data to be ordered. Clustering keys can be defined at table creation, as seen on the slide, or after creation. And to do this, you just need to change that create table command to an alter table command. And the syntax here is really quite simple. A clustering key can also be altered or dropped at any time. And Snowflake recommends not setting up any more than 3 clustering keys and using a maximum of 3 or 4 columns per key, because any more than this and you'll incur quite high costs, since setting up clustering keys does cost some compute in the background, since Snowflake is helping you keep that order that you've set. Now, setting the right columns for a clustering key is really important because they can dramatically impact the query performance. So you want a column that is columns that are most actively used in filters. It needs to have a large enough number of distinct values for effective pruning, but also a low enough number so that Snowflake can effectively group those rows into the same micro-partition. So essentially, we want columns with low cardinality, but not too low. And if you are specifying more than one column in your key, then you should specify the column with the lowest cardinality first. So those benefits, we can see improved scan efficiency, better column compression than in tables with no clustering. And after you've set up your clustering keys, there is no further maintenance required, because once you have specified your key, the maintenance is performed automatically by Snowflake. So now I'm going to move on to the last Snowflake feature that drives improvements in query performance, which is caching. Now, caching is another way in which Snowflake improves performance, albeit it's quite a specific method that may not be available all that often, so I won't dive into it too much today. But essentially, when you run a query, the results of that query are stored in a results cache and will stay there for 24 hours, after which they'll be purged and no longer available for use. There are some conditions for your results cache, and I've listed a few here. So the syntax in your query must remain the same. If you are querying something providing even the slightest difference in result, a completely new query will be run and the cache won't be used. The underlying data in the table can't have changed, so therefore any tables that regularly update live, for example, aren't going to be able to use the results cache. The results of your previous query must still be available, so you must still be within that 24-hour period since the last time the query ran. You can't include any functions that need to be evaluated when executing, so examples of these functions are current date or current timestamp. Micro-partitions must remain the same, so we spoke about reclustering. If you do recluster your data in between executing the same query, the results cache will not be used since the underlying metadata will have changed. So the first image on this slide shows the same query run twice, around 12 minutes apart. The data table has 25 million rows and took 24 seconds when I first ran it on an extra small warehouse. The second time the query ran, it took just 82 milliseconds to return the result, and it didn't use a warehouse this time, meaning no compute resources were used and we weren't charged, which is another benefit. This means that the result has come from the results cache, as you can see in the second image of the query profile, and the query profile can be found in the history pane in your Snowflake browser. So that's all of the features in Snowflake I wanted to discuss. There are a couple other things that I just want to go through before I finish this video, which surround things that you can do to help further improve performance on top of these Snowflake features. So let's talk about subqueries. Subqueries are essentially a query within a query, and here we're going to look at correlated versus uncorrelated subqueries. So an uncorrelated subquery doesn't depend on the outer query. So the subquery can run separately and the results can be used by the outer query just once. Correlated subqueries, on the other hand, do depend on the outer query, which means a different calculation needs to be performed for every row of data in the result, meaning that this can take quite a long time, and so uncorrelated subqueries are much more performant than correlated subqueries. Obviously, sometimes it can't be helped, you do need to use a correlated subquery, but if you can help it, then an uncorrelated subquery will drive much better performance benefits than a correlated subquery. So let's finish off with some final SQL tips. So always try to just select the columns that you require in your select statement. People often default to just selecting star, so selecting all the columns in a table, but this can be much less performant if you do have a lot of columns in your table, and selecting the exact columns you want helps with the micro-partition pruning. Try to filter on columns that are naturally ordered in your micro-partitions. So we spoke through this with the micro-partitions bit previously. Really do try and filter on those columns that are ordered naturally or that you've set up in your clustering keys, because it will allow more effective pruning and it will be more performant for you in Snowflake. Try to group by on columns with a low number of distinct values. The higher the number of distinct values, the more compute Snowflake needs to use, which will cost more and also take a lot longer to run. So try to group by those columns, again with low cardinality, with a low number of distinct values. Do not order by in subqueries. Any order by that takes place in subqueries is pretty much irrelevant because it will just be overwritten by the outer query. But doing an order by in subqueries will cost compute, will take a lot of time, but will not come through in your final results. And try not to use wildcards in your where clause. And we have an example here, and that's because it won't allow the micro-partitions to be used. No pruning will take place because micro-partitions work on a minimum and maximum basis. And if you're using wildcards, Snowflake can't work to a minimum and maximum here. So the more often you use wildcards, the slower your query is going to take to run, because Snowflake has to use a lot more compute because it will have to scan each and every micro-partition for that table. And that's all for today. Thank you so much for watching. I hope it's been really useful. I've enjoyed creating this video. So yeah, I hope there's some things you can take away from it. If you do want access to more Snowflake videos or tutorials or anything Snowflake related, please do subscribe to our YouTube channel, the Information Lab YouTube channel. Check out our Data School blog and check out the Information Lab website, where you'll find lots more resources available to you. But for now, thank you very much and enjoy your day.